Hello everybody, my name is Marius Köppel and this is joint work with my colleagues from the Johannes Gutenberg University of Mainz, Germany. In our research we asked the question whether a machine learning algorithm can solve the challenge of adaptive learning and the individualization of learning paths. We evaluated our method in an online learning platform with a big field experiment. The motivation for this study was that in everyday's life, the computer-assigned instruction are on the rise. If it's the language app you use to learn a new language or any other kind of app which helps you to develop a new skill. On the other side, there are also some concerns about that many of these digital formats do not really work, or in the case of learning a new language, they sometimes claim they would have individualization, but they don't really have. There are a lot of studies done before and after COVID, but also in a well-designed field experiments, and all of them don't really show any kind of individualization or any kind of proof that such formats are working. Why is this? One can ask, what is different from other learning situations? Of course, there's the part of the anonymity. So you're not in front of a teacher or you're not in a classroom with other students. You're just sitting in front of your computer and you're totally alone with the device. On the other hand, all these systems can easily be scaled. So this is a plus. You don't need more teachers. You can just scale it up by having more computers. And most of the systems, they collect a lot of data. So one can think that somehow these computer-assigned assistant instruction can be improved. And in our study, we asked ourselves, how can we improve them that they show individualization? What was the setting of our experiment and what was the goal? So we used an online learning platform for college level learners, which used the platform to prepare for their final high school exam. The ideas of the platform is that there are different multiple choice questions about different subjects. The students can click through these multiple choice questions, and by doing this, they prepare for their final exam. And our idea was that we have an algorithm in the background, namely a machine learning algorithm, which follows each of these students while they're taking the questions to predict the next question they have to answer. We did this over a whole semester from July until November in 2021. How was our setup? These are just numbers to be to give you what we did. So we had 3 groups. So we have a random control group of about 1,500 students. We have an individual group about 1,500 students where we predict for each user on its own learning path the next question. And we have a group-based group about 1,500 students where we just took the mean of all students and used this to predict the next question for a given user. How did we came up with the questions? We had previous work. There was previous work done by Klausmann and Schunk in the same online learning platform, where they just used a simple linear model and did not find any effect on individualization. So we wanted to improve on part of this by using a more complex model, and we did a bit of evaluation, and it came out that having a 1D using 1D CNN layers was a good fit for the task, since the features are somehow set up that neighboring features, if you sort it correct, of course, the neighboring features are from the same domain. Namely, each of these tasks comes with an explanation video, for example, so one can think of combining them, and therefore the CNN layer can find a good combination. And on the left, you see a sketch of our model. So we use two of them. One model for predicting the difficulty of the task. So you say, okay, giving this user, how difficult would it be for this user to answer this question? And then we also predicted how many future tasks the user will do, which would mean which one can loosely translate in the effort, the future effort the user will put in his learning path. Here are just some numbers, what we tried in the grid search to evaluate the model. So we just used the more or less state-of-the-art technology in this field. So but we also scanned through a few of the parameters. So we used different layer size, different filter size. We changed the learning rate. We changed stepwise learning decay. We used different optimizers, different number of epochs. We had early stopping or validation size and different preprocessing functions. How did we then, we did not just predict the tasks and then just assign some of them to the students. What we did was we used these two models to put all these tasks in a 2D grid, where you have on the x-axis the future learning effort, and on the y-axis you have the difficulty of a class. This you can see in the picture with these blue dots. And then on top of this, we used two different distributions to draw from this 2D map. For the effort, we just use an exponential decay, and for the difficulty, we evaluated in a pre-study that having the distribution more or less some kind of inverse lambda distribution, that this is the right thing to do, to don't give them too difficult tasks, but also not too less difficult tasks. And then you can see in this heat map on top of behind the blue points the 2D distribution, where we draw randomly 10 questions from the predictions from the model. However, when we look at our results, and here you can see the control group, the group-based one, and the individualization one, we don't see using a statistical test. We don't see any significant difference between the different groups. However, one can slightly see in this plot that the individualization is a bit better than the control group and way better than the group-based one, but under the statistical test there was no significant difference found. The same is true for the for the results on the performance. So before we evaluated on the effort, and here we evaluated on the performance. So if students do more, not only more questions, but if they answer more questions correct, and also there one cannot really see any difference. Why is this? One can ask. If you just look at the timeline and evaluated the two model performance, one can see that the model performs most of the time really poorly. This can of course be that since we trained it with data from other semesters, that it may be overfitted on this pre-trained data, or that the task is really hard, or you have just a lot of users which are only learning a few days before the exam, which you cannot really follow throughout the time. So you lose a lot. So you don't know a lot of them. You don't have a lot of information from them, and then your average performance is really poor. Another possibility could be that we underestimated our power assumption for our experiment, and that the variance in the different groups, like control group, group-based individualization group, was just too high, that we could not just that we were not able to see any significant difference. However, one can still conclude and learn something from this, in the sense that we can in perform a different experiment with a better setup, in the sense that we just take more students or group the students into high performers. So we first evaluate and look if the student is actually participating in this class, and if not, we don't put them into our trial. Or one can think about having simpler algorithms like trees or some kind of reinforcement learning, which follows only one student, because what we did was we trained our network on all the past students, and then used the individualization for the experiment. But one can also just start with a simple model and only follow one individual student. This might have a better effect, and this would be great future work. So thank you for your attention.